This is lecture 11 on the theme of transitions. It's the last lecture of this whole course. It's a mathematical physics course on quantum mechanics at senior level. First author of the text being used is Davies. It's a two-authored text, Paul Davies and David Betts, called simply Quantum Mechanics. I'm using the second edition. Here's the text. I do this every chapter, every lecture, one chapter per lecture, and each lecture has many parts, as you've probably noticed already. Alright, well, if you want to know more about the course, the chapter titles, all the links to the YouTube uploads of these many, I think, oh god, total now with two courses, must be somewhere around 550 uploads, clips, each clip being about a dozen minutes more or less. Okay, so go to my website, so Prof, short for Professor, Hugo, my personal name, deGaris, family name, .wordpress.com, and then click up the various tabs on the homepage, the front page. So click on the tab deGarisMPC, so M for math, pure mathematics, P for physics, and C for computer theory. So most of these lectures will be on graduate level, so master's and PhD level courses on these three topics, with the majority of them, about 90%, will be on pure mathematics and mathematical physics. So this is a mathematical physics course, and it's the last of this, the last chapter of this text. Okay, now transitions. So from what to what? Well, basically from a time dependent, I mean obviously, because you're changing. So a switch, a transition from one state to another state, and talking about the probability of that happening over a given amount of time. So in that sense, a transition. Now, you may notice it's taken us this long. I mean, here we are now, the last chapter in the book, and the book's fairly thin. It's only about, what, 150? Yeah. In terms of theory, it's about 150 pages with various questions at the back and answers trial. Okay, so we have been dealing largely with time-independent quantum mechanics because it's easier, right? Dynamics is usually more complex than statics, and we've been dealing with what I've been calling the STIE, S-T-I-E. So the Schrödinger time-independent, the I for independent equation. Now, in these coming sessions, 4 sessions per board, 2 squares per session, 8 squares per board. It's a large board, I think 2.4 meters by 1.4, I'm not too sure. A large board. For the next few sessions, we will be dealing with Schrödinger time-dependent, with a D instead of the E, equation. And I'm calling that the STDE, and for short I just call it the STEED, right? STDE, the Schrödinger time-dependent equation. And in later sessions we'll be talking about probability amplitudes for transitioning, for switching, moving from one stationary state to another. Reminder, what is a stationary state? It's a state whose, when you square it, you get the probability density, right? And if that probability density is independent of time, it's not a function of time, it does not change with time, then that state is called a stationary state. Stationary meaning doesn't change in time. Okay? So this time we'll be talking about non-stationary states, wave functions that are an explicit function of time, so there'll be a t for time parameter in the wave function. It'll be psi of, I don't know, r, I guess, position, perhaps spin. Let's say, keep it simple, just say position. So it'll be psi as a function of r, comma, t. Right? There'll be a t in there, explicit t for time. Okay, so it's now a time-dependent wave function. Right? So give an example of a transition of a state to another state. Say you have an atom that's being pumped full of electromagnetic energy. Being a bit vague here, but yeah. And let's say the photons of corresponding to this electromagnetic energy collide using classical images with an electron in the atom, and bumps it up, gives it an extra energy. So instead of it being in a lower energy Bohr, B-O-H-R, Niels Bohr orbit, his model of the atom from 1913, I think it was. So that electron now has moved into a more distant orbit with higher energy, hence an excited state. Okay, so that would be an example of a transition. And you can then have the reverse. So the external energy source, the electromagnetic field, say that's switched off, and then the atom, the electron falls to a lower energy, moves in closer to the nucleus, and the difference, one of the basics of basic laws, conservation law of physics, is that energy is conserved. Energy doesn't disappear. So if the electron has a lower energy, by moving closer to the nucleus, where has that energy difference, where's it gone? Well, in the form, this is Bohr's model, in the form of a photon that's emitted. And the energy of the photon is equal to the energy difference between the higher excited energy and the lower energy of the electron as it moves closer to the nucleus. Okay, so E excited minus E lower equals h bar omega, where the omega is the angular frequency, 2 pi over lambda, right? 2 pi f, the frequency of the photon. Okay, so that's an example of a transition, and we'll be dealing with quite a few in this chapter, in this lecture chapter, same thing. Right? So the essence, like the heart of this chapter, is time dependence, and more concretely, that time dependence will take the form of a time-dependent, perturbing Hamiltonian. Okay. Now, the previous chapter talked quite a bit about perturbation theory, where you have a perturbing Hamiltonian, like an extra term in your Hamiltonian that's usually smaller than the main one, than your H0. So this H dashed, the perturbing Hamiltonian, in this context, for this session, is now a function of time. Okay, so your H dashed has a t parameter in it. Right? So that's sort of the essential idea. Now the basic Hamiltonian that you add the H dashed to, so the Hamiltonian that you perturb, you look on it as a kind of basis, foundational Hamiltonian, the one you start with, if you like, and then you add an H dash, the perturbing Hamiltonian, to it. So you add this to that, okay, as in here. So we know our Schrödinger equation is absolutely basic, one of the most important formulas in all of quantum mechanics. That remains essentially unchanged, right? It's still Hamiltonian wave function equals IH bar d wave function dt. Okay, But now our wave function is now an explicit function of time. You know, time features in the wave function. So here and here. Well, I haven't written it out, but this also be function of R and T. Let's say. So this is assumed to still be valid. Right? But now it's not a STI. It's not a Schrödinger